Hello everyone, I am Rudranath Hajra, a student of Department of Chemistry, Bolpur College. I am going to present my topic entitled Aromaticity. Aromaticity is the property of conjugated cycloalkenes that enhance the stability of the system. Greek word aroma means pleasant smelling, and most of the conjugated cycloalkene has a pleasant odor, so the class of compound are called aromatic compounds. Now, how actually the concept of aromaticity was developed? In 1931, German physicist Heinrich Haeckel observed some cyclic unsaturated compounds are extra stabilized, later named as aromatic compound, and some cyclic unsaturated compounds are extra destabilized, later named as anti-aromatic compound. By ESR spectroscopic analysis, it was found that aromatic compound shows diamagnetic behavior and anti-aromatic compound shows paramagnetic behavior in external magnetic field. Haeckel carried out a series of mathematical calculations and proposed some criteria for a compound to show aromatic behavior, known as Haeckel's rule. Now, what are those criteria? For a compound to be aromatic, the compound must be cyclic, planar, and conjugated. And finally, it must satisfy Haeckel's rule, that is, the compound must contain 4n plus 2 pi electrons in the system, where n is equal to 0, 1, 2, 3, etc. If any compound is cyclic, planar, conjugated, but it contains 4n pi electrons in the system, where n is equal to 1, 2, 3, etc., then the compound is classified as anti-aromatic compound. If any compound does not satisfy at least one of the above three conditions, then the compound is said to be non-aromatic compounds. Now, a comparative study of these compounds. In the first compound, the compound is cyclic, planar, conjugated, and it contains 4n plus 2 pi electron, that is 6 pi electron in the system, so it is aromatic in nature. In the second one, an sp3 hybridized carbon atom is present in the molecule, which results the molecule to be non-planar, and the 4 pi electrons are not fully conjugated in the ring, so it is non-aromatic. And the third one is anti-aromatic in nature, as it contains 4n pi electron in the system and it is cyclic, planar, and conjugated. Now, why this extra stability and extra destability arises? In case of aromatic compounds, the delocalization of the pi electrons over the ring due to the conjugation lowers the electronic energy of the system, hence the system gets extra stabilized. In case of anti-aromatic compounds, delocalization of the pi electrons increases the electronic energy of the system and the system gets destabilized. This phenomenon can also be explained using molecular orbital diagram. Bonding interactions lowers the potential energy of a system and the stability of the system is increased. So, if extent of bonding is increased in any molecular orbital, then potential energy of that molecular orbital will be decreased and subsequently the stability of that molecular orbital will increase. Now, if we study the construction of the molecular orbital diagram for a 3p orbital containing and 4p orbital containing cyclic and acyclic molecule, then we can see in the 3p orbital containing molecular orbital diagram, the cyclic compound, the bonding molecular orbital of the cyclic compound contains 3 bonding interactions, whereas the bonding molecular orbital of the acyclic compound contains 2 bonding interactions, which indicates that the cyclic compound contains greater bonding interaction in the bonding molecular orbital. Hence, the potential energy level of the BMO of cyclic compound lies at relatively lower level than the acyclic one. Same case is observed in case of 4p orbital containing cyclic and acyclic molecule. The energy of the other molecular orbital can be determined by using the concept of number of knots and number of bonding and antibonding interactions present in that molecular orbital. Now Huckel proposed that HOMO of any molecule at lower potential energy level is much more stabilized, and HOMO, that is highest occupied molecular orbital of any molecule at higher potential energy level, is very much destabilized. Now let's feel the electron in the molecular orbital level for the system which we considered previously for our observation. For a 4n plus 2 pi electronic system, if we feel the electrons in the molecular orbital, then we can see that the HOMO of the cyclic unsaturated compound lies at relatively lower potential energy level than the acyclic one, and no unpaired electron is present in the cyclic molecular orbital diagram, which indicates diamagnetic nature, which was previously predicted by ESR spectroscopic analysis. Hence, the cyclic compound of a system which contains 4n plus 2 pi electrons must be aromatic in nature. Now if we feel the electrons for a 4n pi electronic system, then we can see that the HOMO of the cyclic one in this case lies at relatively higher potential energy level than the acyclic one, and two unpaired electrons are present in the molecular orbital diagram of the cyclic compound, which indicates that it will show paramagnetic behavior in external magnetic field, which was previously predicted by ESR spectroscopic analysis. Hence, the cyclic compound which contain 4n pi electron in the system must be anti-aromatic in nature. Now, an alternative method for filling the electron in the molecular orbital diagram easily is Frost circle. In this inscribed polygonal method, a polygon is drawn inside a circle taking one point at the bottom of the circle. Now the total number of corners which cuts the circle represent one molecular orbital level. Now a horizontal line is drawn through the center of the circle. The molecular orbital at the horizontal line is depicted as non-bonding molecular orbital, and the corner or the molecular orbitals below the horizontal line is depicted as bonding molecular orbital, and the molecular orbital above the horizontal line are represented as pi antibonding molecular orbital. Now if we fill electron in the molecular energy level for cyclopropynyl cation and benzene, then we can see paired electron is present in the bonding molecular orbital. Hence, cyclopropynyl cation and benzene is aromatic in nature. In case of cyclobutadiene, two unpaired electron is present in the non-bonding molecular orbital, which indicates that it is anti-aromatic in nature. In case of cyclooctatetraene, though two unpaired electron is present in the non-bonding molecular orbital, but due to the existence of cyclooctatetraene in non-planar tub shape, it is non-aromatic in nature. This phenomenon of cyclooctatetraene is discussed later. Now, here are some examples of aromatic, anti-aromatic and non-aromatic compound. In case of three-membered ring, for the first two compounds, we can see that the compounds are cyclic planar conjugated and it follow Huckel's rule, so they are aromatic in nature. In the second two example, the first one has an sp3 hybridized carbon atom, so the molecule is non-planar, and in the second one, which is a carbon free radical, it contains 3 pi electron in the system, so it does not follow 4n plus 2 pi electronic rule, and it does not follow 4n pi electronic rule, so it is non-aromatic in nature. In the next two compound, it contains 4 pi electron in the system, so it is anti-aromatic in nature. Similarly, the other examples are considered. Now, in case of tropylium anion, it seems that tropylium anion is an anti-aromatic compound because it contains 8 pi electron in the system. But actually, the compound is non-aromatic because the carbon bearing the negative charge goes out of the plane, and which results the molecule to be non-planar. So it is non-aromatic. In case of cyclooctatetraene, it also contains 8 pi electron, but the cyclooctatetraene is not an anti-aromatic compound as it exists in non-planar tub shape, so the p orbitals get tilted from the plane and no effective conjugation takes place throughout the ring. So it is non-aromatic in nature. Now some special type of aromatic behavior is observed. Firstly, homoaromaticity. Non-aromatic compound which possesses partial aromatic character are classified as homoaromatic compound. The sp3 carbon atom present in the homoaromatic compound goes out of the plane and the remaining cyclic part starts conjugation, which leads to partial aromatic character attainment. Homoaromatic compounds can be generated by treating cyclobutadiene and cyclooctatetraene in acidic medium. From a least stable anti-aromatic compound and a lesser stable non-aromatic compound, a more stable homoaromatic compound is formed in acidic medium. So far we have studied aromatic, homoaromatic, non-aromatic and anti-aromatic compound. So their relative stability order is aromatic, then homoaromatic, then non-aromatic, then anti-aromatic. Now the second category is quasi-aromatic compounds. In general, we all know that neutral species are more stable than a charged one. But quasi-aromatic compounds predominantly exist in charged form rather than its neutral form because the compound attain extra stability due to aromaticity attainment in polar form. Bicyclic conjugated bicyclic compound will be quasi-aromatic if both the rings attain aromatic character after the pi bond migration. In the following two examples, we can see that pi bond migration can take place in two ways, which will generate two types of polar compound. But pi bond migration will take place in such a way that the compound will predominantly exist in that form in which both the rings get aromatized and the system gets extra stabilized. Now quasi-aromatic character can be observed in three types of compounds: cyclic hydrocarbons, cyclic ketones and azulene. In case of cyclic hydrocarbon, in the first two examples, both the rings get aromatized due to polarization. So these two compounds are classified as quasi-aromatic compound. In the second two example, both the rings are not aromatized after the pi bond migration. So they are non-quasi-aromatic in nature. In case of cyclic ketones, the pi bond migration may take place in such a way so that the more electronegative oxygen atom bears a negative charge and the ring bears a positive charge. If the ring bearing positive charge contain 4n plus 2 pi electron in the system, then the ring become aromatic and the compound is classified as quasi-aromatic compound. Here are some examples of quasi-aromatic cyclic ketones. Now quasi-aromatic compounds, due to its existence in polar form, it possesses some special characteristics that are dipole moment of quasi-aromatic compounds are very high. Being polar, quasi-aromatic compounds are soluble in polar solvents like water. Cis-trans interconversion is observed in case of quasi-aromatic compounds. Now why cis-trans conversion is readily observed in quasi-aromatic compounds? In the following example, we can see that the nonpolar cis form is least stable due to the steric repulsion of the two methyl group present in adjacent position, in same site actually. Due to polarization, both the rings get aromatized, but the repulsion of the two methyl is not completely removed. It is removed in some extent because the double bond is converted into single bond, so the bond distance is increased. So repulsion is decreased in a little extent, but not fully removed. So the polar cis form is relatively more stable than the non-polar cis form. Now after the pi bond migration, the double bond is converted into single bond, and rotation around single bond is favored in room temperature, which leads to the formation of a polar transform, which is the most stable in the following three compounds, because the steric repulsion of the 2-methyl group is fully removed and both the rings are aromatic in nature. That is why cis-trans conversion of quasi-aromatic compounds is readily observed. Now the last quasi-aromatic compound, that is azulene. It is a special type of quasi-aromatic compound in which a 7-member and a 5-member ring is fused together. In the polar form of azulene, the 7-member ring exists as propylium cation and the 5-member ring exists as cyclopentadienyl anion. Azulene is dark blue in color, and the name of azulene is given according to a Spanish word azul, which means blue. It is an isomer of naphthalene. So if we compare the relative stability of naphthalene and azulene, then we can see that for naphthalene both the rings contain 6 pi electron, and for azulene both the rings contain 6 pi electron, but in case of naphthalene it is neutral in nature, but in case of azulene polarization is required for aromaticity attainment of the two rings containing 6 pi electron, and neutral species are generally more stable than charged species, so naphthalene is more stable than its isomer azulene. Now the last class of compound, that is annulenes. Annulenes are monocyclic systems with alternate single bonds and double bonds. The number in the bracket in the name of annulenes represent the number of carbon atom present in the skeleton of annulene. Cyclobutadiene, that is 4-annulene, is the smallest annulene which is anti-aromatic in nature. Benzene, that is 6-annulene, is aromatic in nature and it is the smallest aromatic annulene. Cyclooctatetraene, that is 8-annulene, is non-aromatic in nature, as we have studied that it exists in non-planar tub shape, so effective conjugation does not take place throughout the ring. In case of 10-annulene, it seems that it is aromatic in nature because of presence of 10 pi electron which satisfy Huckel's rule, but actually it is non-aromatic in nature. Because of the repulsion of the two junction hydrogen, the p orbitals of the 10-annulene gets tilted from the plane and no effective conjugation takes place throughout the ring, which leads to non-aromaticity of the compound. But if we substitute the two hydrogen, or if we replace the two hydrogen by a methylene group or oxygen atom or NH group, then that group goes out of the plane and the 10 pi electron start conjugation throughout the ring, which leads to aromatic nature of the compound. In case of 12-annulene, it seems that it is anti-aromatic in nature as it contains 4n pi electron in the system, but due to the steric repulsion of the junction hydrogens, 12-annulene gets the non-planar conformation and it is non-aromatic in nature. In case of 14-annulene and 18-annulene, it is aromatic in nature as the ring size is increased and the junction hydrogen repulsion does not disturb the planarity of the system. In case of 16-annulene and 20-annulene, it seems that they are anti-aromatic in nature as it contains 4n pi electron in the system, but they are actually non-aromatic in nature because the number of carbon atom and the ring size is increased, so the ring is flexible enough to exist in non-planar form so that it becomes more stable non-aromatic compound than anti-aromatic compound, which is the least stable in the in case of if we compare anti-aromatic, aromatic and non-aromatic. So 16-annulene and 20-annulene are non-aromatic in nature as they exist in non-planar form. Now these are the references from where I collected the informations. My acknowledgement, and thank you for hearing me with patience.